Hello, Brian Miller-Hicks here, continuing my series on engineering geology, and now I'm going to talk about geotechnical parameters. So this has to do with rock and soil, the properties that can be ascribed to different types of rock masses, different types of soil, uh, the whole geologic range of conditions which can be quite variable. So looking at this slide, upper left, Torrey Pines beach cliffs, that's exposed bedrock, of course, sandstone and shale, two very different rock types deposited under different environments during the Eocene. The sandstone in a higher energy seashore wave environment, the shale or mudstone deposited in quieter lagoonal type waters. So because these rocks were deposited under different environmental circumstances in different energy regimes, their properties are quite different. Mudstone or shale is fine grained, of course. Sandstone is coarser grained. Sandstone may have higher strength. The mudstone may be more prone to weaker type rock properties. Upper right, we have an ancient landslide in the near the uh, Mission Creek Regional Park, Mission Valley Regional Park. Excuse me. I'm sorry. It's Mission Trails Regional Park. Okay, I got it now. So different soil and rock conditions present a different kind of issue or problem for engineering geologists. Lower left, a rock mass that's highly jointed and fractured, where the rock itself may be high strength, but the joints and fractures control the effective strength of the rock. Where you have a fractured rock mass, of course, it may be more prone to breaking up along distinct and discrete joint or fracture planes. And lower right, we have what's called normal heights clay, Pleistocene age clay, claystone, very stiff, very expansive, very plastic. By expansive meaning, if you add water to this material, it will swell. Presents, again, a different sort of problem to the engineering geologist, whether you want to go through it with deep foundations or remove it and replace it with something else, or perhaps mix it with a lime mix that might strengthen it. So let's look at general physical properties of soil and rock. Unit weight has how heavy it is. Density, of course, is weight in relation to volume. The more weight you have and the smaller volume, the more dense it is. The strength properties of rock and soil, the important properties, of course, are friction and cohesion. Shear strength is the resistance of soil and rock against deformation. Then we have porosity and permeability, which have to do with the ability of rock and soil masses to conduct water. A permeable rock or soil has the ability to conduct water fairly easily. An impermeable rock or soil, of course, can impede the progress of the movement of water. Porosity has to do with the percentage of voids or pores in the rock and soil mass. The more porous it is, the more voids that rock can be stored in. Durability and hardness, pretty much self-explanatory. Fractures and joints, I sort of mentioned that in the previous slide. So when we talk about the process by which sediment or soil can become rock, it happens over a long period of time where you have sediments that are increasingly buried at depth. The more depth there is, the greater the burial depth is, the more likely that soil or rock mass can increase in density and strength through the processes of compaction, consolidation, getting rid of water, and cementation, iron cements, calcium cement, and so forth on its way to becoming rock. So increased density and strength, increased depth of burial can decrease porosity or void ratio. So you have a soil material here. It's saturated, it's got water-filled pore spaces. Then you subject it to compaction by pressure, burial pressure, or perhaps metamorphic or tectonic pressure. It will compact this sediment into a sedimentary rock. And cementation takes place by virtue of water that carries chemicals and cementing material within it, like calcium carbonate or iron oxide. Circulation of mineral-bearing groundwater can can promote the lithification process and cement particles of soil and rock together. Shear strength is defined as the shear resistance of a rock to failure, and I'll show you some ways of testing shear resistance or shear strength. You have electrochemical bonding, and under stress, of course, you can have elastic deformation, dissolution in plastic flow. That can happen readily under deep conditions where rock may lose its ductility, may lose its brittleness and become ductile and therefore deforms plastically. So shear strength has components of cohesion, which is interparticle friction, cement filling pore spaces, mineral bonding, electrostatic forces. All these forces contribute to the cohesion of rock and soil. Sands generally have lower cohesion than clays, but higher friction, cementation, and strength. Silts and clays are more cohesive. There's more intragranular chemical bonding. There's higher electrostatic forces. What affects cohesion? Well, it's affected by water content. Higher water content, lower cohesion. You determine cohesion in the lab primarily from a direct shear test. So when we're testing soil or rock, we can use a variety of test equipment. One is the unconfined compression test, wherein take a cylinder, a sample cylinder of rock or soil, and just press down on it, compress it. At a certain compression or a certain pressure, this cylinder sample will fail, and that will give you its compressive strength. Fairly simple test. Here you have a compression test in action, where you're pressing down on the cylinder of material, and here you see sort of a fracture or crack in the sample. That is the shear failure surface. That's where it fails, and that's typically what it can look like, is sort of an angled fracture. Other shear strength testing, triaxial, where you have not only compression from top and bottom, but you have compression on the sides. It's pretty expensive investment to get a triaxial shear strength test set up, so it's not commonly used. Direct shear is more widely used, and I'll show you what that is. Here's a direct shear setup testing equipment. It's under a normal load vertically, and you place a sample, usually an inch thick or so, a couple inches in diameter. You put perforated plates on top and bottom for drainage, and then you load this sample laterally or horizontally so that it then fails along a discrete horizontal plane represented by the dashed line, and the force at which this sample fails is its measured shear strength. Okay. So here's a plot of data from a direct shear test. The higher the normal stress is, the more shear stress it's going to take to fail that sample. So you press down harder and harder on it, it's going to take more force to fail that sample. Here is a method of measuring shear stress and normal stress during a direct shear test. So this T sub F is the maximum shear stress the soil can take without failure under a given normal stress. This axis is normal stress, this axis is shear stress. This gives you two properties of the soil. It gives you the cohesion, the intergranular stick-to-itiveness of the material, and it gives you a friction angle. So let's say you have a sand. The sand would have low cohesion, so you'd have cohesion down here maybe, but the friction angle would be steeper because it's got more friction in intergranular contact. A clay would have higher cohesion but a shallower friction angle. So again, you have the failure envelope. This is what's called Moore's circles. It's a plot when you're plotting normal stresses and you're subjecting a sample of soil to normal stress and shear stress. Again, this is the curve of shear failure. Once this circle exceeds or goes beyond this line, you have a sample in failure, like shown here. As loading progresses, the Moore's circle becomes larger and larger and larger. Finally, failure occurs under certain normal stress and shear stress, and you get a failure of the sample, whether it be soil or rock. So this is a basic graphical analysis tool that's used to process the data you would get from a direct shear test. So let's look a little bit at some typical compressive strengths of rock and soils. 1 MPa is a megapascal, which is 145 pounds per square inch. So you have a scale here ranging from 0 to 6, ranging from extremely weak to extremely strong. The compressive strength will range from 0.25 to greater than 250 megapascals. And here you have a field estimate of strength. Soft, weak materials, you can put your thumbnail in it and put a dent in it. Very strong, extremely strong materials, you can only chip it or break it with a geological hammer, maybe stronger than concrete. Examples of weak material include maybe chalk. Examples of very strong, extremely strong material may include fresh basalt or quartzite or granite. Here's another handy chart. I won't go into it too much. So you have soils and you have standard penetration tests. These are blow counts. So you're looking at 30 to 50 blows per foot of penetration of the sample while you're sampling in a drill rig. You're pounding the sample rod with a 140-pound weight conventionally, drop 30 inches to get a blow count. So a blow count of 30 to 50 is pretty dense. In rock, You may not use blow counts so much because it's so strong that your sampler may just bounce up and down on top of the rock. Okay, now let's talk a little bit about problematic soils. This refers to a very unusual soil or unusual soils. You have expansive clays, including montmorillonite. When you add water, it'll swell. It's got low shear strength. If you put it in direct shear, it fails pretty easily. And you have something called quick clays. And I included a link, I hope, to a very interesting little video showing what happens when these quick clays get shaken around. They're saturated, they're very weak. They've been deposited under glacial conditions. This is a quick clay under fairly stable conditions. Then when it gets shaken up, it just becomes chaotic and fails and flows. Landslides slip along clay plains typically, which again have low shear strengths, maybe high cohesion, but very low friction. They may have friction angles of only 5 to 7 degrees, which is pretty low friction. And if you press down on clays, they can also consolidate. As water escapes, they become lower volume, but denser in density. When you consolidate or press down on clays and they compress, that may lead to settlement of surface layers and settlement of ground up above, which is not a good condition to have. Here's the quick clay video as promised that you can click on. Hopefully the link will take you there. Here's some more problematic soils. Conglomerate, very gravelly soils, very highly cemented soils. We have in the San Diego area, we have the Stadium conglomerate and we have the Poway conglomerate. Large cobbles which were deposited under alluvial conditions by large flowing rivers, high energy rivers. In the past, we got a lot of Eocene conglomerates. And then through time, of course, these gravel bars or channel deposits became consolidated and cemented, and they're very, very tough and strong. They're extremely difficult to drill through. You can chip away at it, but trust me, these have high shear strength and high bearing values. Let's talk a little bit more about rock strength per se, okay? So you have fresh to moderately weathered rock. You can break it by hand. Fresh rock has pretty high megapascals, 400 plus. You use the uniform classification system for soil and rock. You use them as a guideline for strength of rock. Strength of rock, of course, is very important for many, many structures. Rock slopes, you want a strong rock. When you're tunneling through rock, you want your rock ideally to be hard and strong and not highly fractured. Mining, of course, the same thing. You want it to be strong, not highly fractured. And this runs into safety issues as well. When you have people down there in a mining situation, you don't want to have rock failures or rock bursts. There's something called the Geological Strength Index, which rates overall rock mass conditions. The more fractured and pervasively fractured a rock mass is, the weaker or the lower strength it's going to have. Here's a geological strength index. Hard to read, but you have the weakest rock down here, laminated and sheared. and you have the strongest rock up here, intact or massive rock. So let's talk about rock joints or fractures. You can determine friction of a rock mass in between the fractures by direct shear testing. Rock joints or fractures will affect permeability, movement of water. Hydraulic conductivity is the property that allows a rock mass to conduct water over large distances over time. So all these parameters depend on your joint geometry, roughness of the joints. If you have a rough joint, it is less likely to slip or fail. If you have infill, like clay fracture filling, clay filling the fractures, that can lead to instability situations and even failure of blocks along these infills of clay. As you see here, fractures infilled with weak materials, you have lower shear strengths and lower resistance to sliding. Now, in the lab, it's pretty hard to analyze a rock mass just from a small sample. As I've mentioned, a large rock mass strength properties and other properties are determined by the overall fracturing, the overall density of fractures, number of fractures, how close the fractures are spaced, and whether or not they're rough or have clay, weak clay infillings. When you have the weathering of rock, you can start with dense, unweathered rock through time, physical processes, and chemical processes. The granite, in this case, can weather. Feldspars included in the original granite rock are notorious for weathering to clays, and therefore the rock mass becomes more weathered, weaker through time. Here we have a fresh excavation where we have decomposed granite, which is still pretty dense and has good bearing values, but it's not as dense and strong as fresh granite, for example. Now, I was talking about infilling material within fractures. Here's an example of some green clay chloritic type material that's infilling this fracture in a granite rock boulder. So here's the fracture, this line here, and here's the greenish clay material, which if oriented adversely in accordance with your slope may cause failure problems. How do we use rock in construction? Various ways. We can use crushed or quarried rock. Here in San Diego, we have a coastline, so we use a lot of large rock, and we call it riprap to protect coastal bluffs. We have a lot of very steep, very high sandstone coastal bluffs, so we can armor some of these bluffs by placing rock, large rock against them. We can build jetties and groins and coastal protection structures. It has to be very durable and very available. Here in San Diego County, we use, preferentially, we use the Santiago Peak Formation, which are metavolcanic rocks, very dense, very durable, very strong. We use sand and gravel and concrete. We want to avoid certain materials like gypsum and clay, which can weaken concrete aggregate. And we use rock as dimension stone to build special structures like sidewalks, facing, sculptures, etc. Okay. We use rock, crushed rock, as road aggregate, as you can see here. Here's a photo of riprap being used in Oceanside to protect these apartments from the strength and power of waves. Obviously, the waves crash against this rock and lose a lot of their energy. Just a photo of different types of concrete aggregates. Dimension stone used in special building opportunities. Slate for patio flooring or walls. Marble used for various purposes, and sandstone